Okay. So we discuss, if we go over this table that I mean the slides that we have here, we discuss about the reaction rate, which is just the change in the concentration over change in time. So if you're going to write the reaction rate, if it with respect to the reactant, you should always put a negative sign. If it with respect with the change in the product, okay, it's just as is. And the main reason why you use a negative because the final concentration of your reactant is always less than the initial concentration, which will give you a negative value. And there's no such thing as a negative reaction rate. So that's why you have to multiply it with a negative. We also discuss about the expression on how we're going to relate the rate of reaction with all the species that are involved in the reaction. So the way that we express this is the reaction rate is just equals to the reciprocal of whatever is the stoichiometry of your reactants or products, and compare it with the stoichiometry, the reciprocal of your stoichiometry with the other reactants and products. So you can only apply it if you're dealing with the reactants and products in a given reaction. So you want to relate how the decomposition of the reactants in comparison to the formation of the products. Okay. And we also discuss about instantaneous rate and reaction rate or the average rate, how they are what we call different and they the same in one way or another. We solve some problem. And I think, if I'm not mistaken, we end up with the rate law, how the rate law is being written. And we all know rate law is just with respect to the effect of the concentration of the reactant to the reaction rate. So how is the rate law different from the reaction rate? Usually you have a rate constant. You have this so-called K. And the rate law, you can only determine it experimentally. Okay? So whenever you have a rate law, you have, I have to, so the way you have the rate law, so you have the reaction rate there, and then you have the rate constant, and then maybe one of the reactants raised to a certain power times the other reactant raised to a certain power. So M and N there are what we call your reaction order. So how do we determine the reaction order? Is by determining, by changing the concentration of A while B is constant, what happened to the reaction rate. So the way that we look at this is when rate is multiplied by 1/2, your M is -1. So whenever you double the initial concentration and you see the rate changing, it has a corresponding reaction order. Okay, so you double the concentration, the rate is what we call 1/2, so your M is equals to -1. You double the concentration, the rate remains the same, the reaction order is 0. You double the concentration, the rate is double, your reaction order is first order. You double the concentration, the rate that you have is 4 times, then your reaction order is second order. Okay, so I'm going to what we call pose an additional discussion about this given problem, because some of these we already solved. So the next thing that we're going to do today is integrated rate law. So how is this different from what we have discussed so far? Okay, so when we're talking about integrated rate law, we're looking at the relationship of the reaction rate with time. So the rate law, what's the relationship that we have with the rate law? Usually, okay, it's the relationship of K with the concentration of the reactants. Now, we can also use, okay, that rate law to determine the concentration of reactants at certain time. So as mentioned here, the rate law tells us the relationship between the rate and the concentration of the reactants and the catalyst. Now, to find the concentration at various times, we need to use the so-called integrated rate law. The form used depends on the order of the reaction. So remember, we have what? We have a reactant, and it's going to produce a product. If we're going to look write the reaction rate of that, this is equals to what? The change in the concentration of A times delta T, and this is what? Minus, right? Now, how are we going to write this in terms of rate law? If it's, let's say, first order. So rate is just equals to K times the concentration of A raised to the 1. Now, what can you say about these two equations? In one way or another, they're the same. How are they the same in one way or another? Anyone?
They both determine rate.
Okay, they both determine rate. So what does this mean? What if we're going to combine the two of them? Okay, so if you're going to combine the two of them, what do you have? So you have this on one side and this on another side. Does that make sense? Is this magic? Okay, so how did I end up with this relationship? So I just put it out. There's a rate of reaction here with respect on the change in the concentration of A over change in time. And there's also a rate of reaction here in terms of the rate law. So those two are the same. So what if I combine it? Okay. And then what do? I differentiate it. What will happen? I'm going to put all A on the same side, or we could say if I differentiate it in terms of the one that we have here. So this is K of A, and this side will be D of A over D of time. It's messing again. And what do we have from learn from math? We can combine this on one side, all of this so-called A. Okay, so I have K negative T of T, and then on one side I have D of A over A. And what will happen here if we're going to do an integration? Okay, so I have a negative K, I integrate this one, D of T, so initial T until a certain T, and then I'm going to integrate also the other side here, the initial concentration of A to the concentration at a certain time, okay, to give me this one. This is just A. So out of this, you can get a relationship that is similar to this one. Okay? So this is just what we call the first order integrated rate law, or integrated rate law for first order. And if we summarize this integrated rate law, the one that I have performed is for any first order reaction. So you end up with this one. For a zero order reaction, you will have it like this one. So integrated rate law just means this is the equation that you use to determine the concentration of the reactant after a certain time. Okay, so if we're going to look at this is the concentration after a certain time. This is the initial concentration. K is your rate constant, and T is the time after a certain after the reaction is what we call started, or that's the time that corresponds to the concentration after a certain time. Now, if it's a first order reaction, it is ln of A after time over initial concentration equals to negative K T. And then in the second order, it is the reciprocal, okay, of the concentration after time equals to KT plus 1 over the initial time. Now, this is very important to you that depending on what's the order, there are different equations that you're going to use in terms of the integrated rate law. Okay? Now, just remember, integrated rate law, this is the law or the equation that you use if you want to determine the concentration after a certain time, or whatever information that you have given the other information. So for instance, you're given, oh, this is the concentration after given an initial concentration of this. This is the rate law or constant. So what will be the time that it takes for this reaction to have this concentration? Now, to help you understand this thing, let's solve problems on this. So for instance here, so you have here cyclopropane used as anesthetic. The isomerization of cyclopropane to propene, as shown here, is a first order with a rate constant of 9.2 per second. So that's 9.2 per second. If an initial sample of cyclopropane has a concentration of 6 molar, what will be the cyclopropane concentration be after 1 second? Now, it has to tell you what type of first order reaction it is. Because as I have shown you in the previous table, each order has their own integrated rate law. So if I use what we call the wrong rate law that I have here, it will give me a wrong value. So since it is a first order reaction, so you can always go to this equation. So based on the given problem here, what are the information that is given? Anyone?
K.
Okay, K is given. What else?
T.
T is
The
given.
time.
Okay. What else? Which one is given? AT or AO? The initial or the time? The concentration after time.
AO.
Okay.
The
So the
initial.
one that is given is the AO because you have an initial concentration. So once you have that, all you need to do is plot. So ln of AT, that's the one that you're looking for. And then you have AO, that's 6 molar. And then you have 9.2 per second. And then you have 1 second. Right? So we could say this part here is just negative 9.2. Because 9.2 times 1 is 9.2. Now, how are we going to remove the ln here? Anyone? How are we going to remove the ln?
You raise it to the E.
E. So So you need to get the corresponding e to the negative 9.2. So this becomes AT over 6. And what is e raised to the negative 9.2? So what's the value of this? Anyone? What is e raised to 9.2?
Is it 1.01 times 10 to the power negative 4?
Okay, so 1.01 times 10 to the negative 4. And we cannot get the AT here because all we need to do is what? Cross multiply, right? So multiply it by 6. So 80 now is 6.06 or 6.1 times 10 to the negative 4. Analyze.
So if we have a question like this on the quiz or on the exam, it's going to tell us what order the reaction is.
It should be able to tell you what order it is.
Okay, thank you.
Okay, so the important thing that you need to remember here is what is the corresponding equation that you're going to use. So you go back to the previous slides that we have because it tells you for every order of the reaction what integrated rate law equation that you're going to use. And if I'm not mistaken, this information will be given to you in your exam. You don't need to memorize them. Okay? So if you're going to have this thing here, so if it's the first order as the one that is mentioned here, so you have to use the first order. And then the next thing that you're going to do is, okay, what are the information that are given? So it just happened here that you're given K, you're given T, you're given the initial AO. So the one that you're looking for is A over T. Now, corresponding to this, what we call integrated rate law is the so-called half-life. So if we're going to tackle this definition of a half-life, we could just say that's the time required for the concentration of a reactant to decrease to half of its initial concentration. Okay, it's the time it takes for the reactant concentration to decrease to 1/2 of its initial value. So if you have what we call an integrated rate law, all you need to do is you substitute your A of T with 1/2 of AO. And you're going to get there a corresponding half-life equation. And once again, you don't need to memorize them because this is already given to you. So the half-life that you have is this one. So this is the T1/2 that you have. Now, you may ask yourself, how did you end up with getting the first order there to have a half-life of 0.693 over K? Anyone? So remember, how's the first order written? First order is written as ln of A T over ln of AO, right? Equals to negative KT. So where do you think that 0.693 came from? How did we end up with that one coming from here?
The ln.
Okay, the ln. So if we're going to do the thing that we have here, so what does it says earlier in the slide? We substitute a of t with 1/2 of a of t. So if we're going to end it up, we will have like this, right? So if I'm going to simplify everything here, I can divide both of them by k. Now, how can I eliminate this one? Or before I do this multiplication, how can I eliminate negative k? The negative here. Can I just make it like this? Are they the same?
No, you have to put it on the other side of the equation.
No, I mean, is this equation the same as this one?
Oh, yeah. Yeah.
Because I just want to eliminate the negative. So how will I eliminate the negative? What did I do? I just
Flipped it.
flip it. So now that I have this one, I can remove here, okay, the k by dividing both sides by k. Because the t that I have here is definitely what? My t 1/2. Okay? So when I do that, what will happen here? So this will become, because this is what? Initial concentration over 1/2 of initial concentration. So if I'm going to simplify, that is on straight what? ln of 2. So what happened to this equation? This just becomes ln of 2 over k. And I want you to look at your calculator. What's the value of your ln of 2? Because that's how you get the 0.693. So what can you say about the half-life of the first order reaction compared to the second order and the third order and the zero order? What's the difference of this compared to the other two half-life? Anyone? Even if you don't know anything chemistry, if you're going to look at the half-life equation, you will see the first order has a different equation compared to the zero order and the second order. What is
There's
that?
no A.
There's no A. So the first order reaction doesn't depend on the half-life of the first order reaction doesn't depend on the initial concentration. It just goes to its what? 0.693 divided by
K.
the rate constant. Everybody got that? You don't need chemistry to catch that. All you need is what? Common sense. Because here you see an A here you see an A0 or A initial concentration, but you don't see here, they all have K. Okay, so that means this would be the difference that you have there. And let's try to solve a problem on half-life. So these are really what we call pretty straightforward thing. So you have this equation wherein your ammonium nitrite is what we call unstable because ammonium ion reacts with nitrite to produce nitrogen. So in a solution that is 10 molar in ammonium ion, the reaction is first order in nitrite ion, and the rate constant is 3.0 times 10 to the 3. And you are asked for the half-life of the reaction. So, right? Then, you can always put what? The 0.693 divided by
3 times 10 to the third.
and you will get the half-life as equals to what?
Uh, 2.3 times 10 to the uh, uh, power of -4 or -3.
Okay. I get -4. Anyone? What did you get?
I got the same thing.
Okay. So analyze. Question? Question? Pregunta? So all you need to know is the equation which will be given to you. So most likely you will have a table like this one that contain the rate law, integrated rate law, and the half-life. So question so far before we go with how do we plot the integrated rate law? So if you're going to look at here, all of them will have this. What is y equals to mx plus b? Anyone?
Line intercept form.
Okay. What is the y equals to mx plus b? That is your equation of the line, right? Now, the thing here, you should be able to determine based on a plot whether you have a first order, second order, or a zero order, because all of them assume the equation of the line. Okay, so let's go into zero order. So if we have a plot here, what is in the x-axis? Anyone? If you're going to make this an equation of a line like this, so what is in the x-axis here?
The constant.
Hmm? Anyone among the 54 students? Which one is
The
the x
constant.
here? Okay, is it the constant or the time?
The time.
Okay, so that's the time. Now, what is the y value? Okay, so the y value is the concentration, that one. Because what you have is y equals to mx plus b. So your y value there is the concentration after some time. Now my question now is, how does the plot look like? Will it be A like this, B like this, C like this, or D like this? Choose. Will it be A like this one, B like this one going up, C, which is just a straight line here, and D is a straight line also? Anyone? The answer is A. What's my guide of it being A? Look at the equation here. You have a negative slope there. So that means the value there is decreasing. Remember, this is what? The concentration of a reactant with time. So with time, they will decrease. That makes sense? Everyone? Okay? Now, what will change if I make it a plot of a first order? So what is my X value here? Anyone? If I
Still the
have now a
T.
first order, what is my X value here? Still the time. But what is now my Y value? I want you to look at here. How are you going to make this in the form of this? So how will this form, if you break it down and make it in this form, what will be the Y value that I'm going to put in the Y-axis? If it's a zero order, it's the concentration of A with time. This one is the concentration of A, Ln, with time. Because if you're going to break it down, this is how it looks like. Y equals to mx plus b. Does that make sense? Why I end up with this one? Now the question is, how does the plot look like? Following the choices that we have here, A, B, C, and D. How does the plot look like for a first order if you plot time versus ln of A with time? Anyone? What it will be? Will it be like A going down, B going up, C straight line, D another straight line? These are the type of questions that usually being asked. If you're asked to plot a first order, which will be the plot looks like, and then you have their different plots, and you will be asked, okay, which is the correct plot? Or if I ask you, which is the correct plot for first order reaction? So you have here, like this one, like that, and then you have here, like this one. So if you have there A, B, and C, or you have here like this. So those are the type of question that you can be asked. That's why I'm spending some time, at least in this portion. So since you also have a negative slope there, you expect the first order to be like that. Similar to the zero order, the only difference, you have an ln here, and this one you have an A, the concentration right away. Now we have that. How about the second order? How does the plot look like? So T is still the X value. Now what is the Y here? Okay, so this is the Y equals to mx plus b. So right away you could say it's the reciprocal of A with time. Now how does the plot look like? Is it A decreasing, B increasing, C straight line, or D straight line going down? If you have what we call the first order or the second order. So again, you look at the slope here. It's positive, so It's going up. You're going to do this in your experiment. I think, if I'm not mistaken, experiment 16. You have a set of what we call order time versus the absorbance, and then you're going to plot them. Okay, plot in the first order, the second order, and the zero order, the one that gives you the highest R squared. That's usually the order of the reaction. So we usually have questions like this in the exam and in the final exam. Okay, so the idea here is you should be able to identify the plot for a first order, zero order, and second order integrated rate law. So this is how usually a second order plot would look like. It's the reciprocal there versus time. So these are the same set of data. Okay, so when you plot the set of data in first order, wherein you use the ln of the concentration, this is how it looks like. So if you put it, the R squared is not really linear. But if you put it in a straight order, what we call a second order thing, so it's almost linear. So between the two, the second order is much preferred than the first order. So that means the reaction follows the second order. Is that clear? Can you assure me at least what, 3 points in the exam? Now the next thing that we're going to do is we're going to relate K with temperature. Okay, so rate constant with temperature. So if we're going to look at it, the rate constant depends strongly on the temperature. Now the question is how? How does this happen? That the rate constant depends on the temperature. So we go here to an explanation, the so-called collision theory. So if you have a collision theory, what does it mean? For a reaction to take place, there should be a collision between the reactants. Now, what happened when the temperature increases? What is the probability that the collision will happen? Okay, so we all know from your what we call gas law or the kinetic molecular theory, as the temperature increases, the movement also increases. Okay, so the way that you're going to do this, the higher the temperature, the greater is the movement of the reactants. So the greater the movement, the higher is the probability of collision. In real life, how are you going to compare this? When it is likely that you're going to hit another car, if you're running slowly or you're running faster, or you're running fast. So most likely you will have collision if you're running fast, right? If you're running slowly, most likely you will not have any collision. So the same thing with the molecules. If the temperature increases, so they are moving at a much faster rate, so most likely they will hit one another. Okay, so the collision theory assumes that reactant molecules must collide with an energy greater than a certain minimum value and with proper orientation. So they just don't collide. The collision should be, we could say, with proper orientation for it to be effective. Now, the minimum energy that you have there, that's what we call the activation energy. So for you to form a reaction, the collision should be enough to overcome the so-called collision activation energy. So activation energy, that's the minimum amount of energy required to initiate a chemical reaction. And before we go about this collision energy, let's look at what are the factors that affect chemical K with respect to the temperature. So if you're going to look at the rate constant, we know that it's the small k. And the rate constant, we could say, can be given by Z times F times P. Okay? So here you will see how temperature really affects rate constant. C is the collision frequency. Now, what can we say about the collision frequency when the temperature increases? It also, what? What happened to the collision frequency if the temperature increases? So as the temperature increases, okay, so it also increases because as the temperature increases, they will move at a much faster rate. So if they move at a much faster rate, most likely they will collide. The frequency of collision increases. So that means if C increases, K increase. Now the second factor that we have here, fraction of collisions with the required with the minimum energy. So as you could say earlier, as the temperature increases, they move faster, the molecules move faster, so the collisions also increases. So just like C, your F also will increase, giving you an increase in K. So the only one that is not really affected directly is the orientation factor. But the movement of the molecule, which makes it faster, most likely will result or give you the proper orientation when they collide with one another. Okay? So we could say among the three, this one has a net direct effect. This one is a little bit what we call indirect, but it's still effective. Okay? Because what is this proper orientation that we have? So for instance, you have these molecules. So when we're talking about proper orientation, okay, the molecules should react in a certain orientation. So for instance, you have a chlorine gas reacting with NO. So for them to be effective, the nitrogen must be the one approaching the chlorine molecule. Okay? Because if it's the oxygen, just like this one, what will happen? They just collide. But their collision is not effective. When I say not effective, whatever they are before the collision, they're still the same after collision. For the collision to be effective, whatever they are before collision is different after collision. So here, after collision, what will happen? You form NOCl. So you have NO here reacting with Cl2. So at the end here, you form NOCl. Here, whatever you have NO and Cl2 at the beginning, that's still the one that you have after the collision. So this is the one that has this proper orientation. This is the one that has this so-called effective collision. Now imagine if they're moving at a much faster rate. So most likely, they will have effective collision. Okay, because the molecules are moving itself. So that's one of the three conditions that you have there that affects this what we call rate constant. Okay. Now, how about this activation energy? How does it look like? So, synonymous or what we call the giving evidence to the so-called activation energy is the so-called transition state theory. So this explains the reaction resulting from the collision of two molecules in terms of activated complex. So what does this mean? Whenever there's a collision, they will go through a transition state. And the transition state, that's the one that is what we call unstable. Now the question is, why are they unstable? Why do you think the transition state shown here in this figure is unstable? Anyone? What dictates stability here? Why do you think the transition state that we have here is unstable? So when we say the transition state, this is the one.
The amount of
Anyone?
energy required.
Okay. They are unstable because the energy, that's the highest one. Okay. So if you're going to look at this stability, when are you relaxed as a person? When you have a lot of energy or you have less energy? Ask yourself, when you're excited, is that a stable state or unstable state?
Unstable.
Unstable, right? I'm so excited. And then after that, you realize, oh, Valentine's is gone. Okay? So whenever someone is unstable, usually you have high energy. So the same thing with the molecules. Okay? A molecule is more stable if their energy is low. So what you have here, you have NO reacting with Cl2 or colliding with CO2. So you have the transition state theory. It's explained, okay, that it's resulting from the collision of two molecules in terms of the activated complex. So this is your activated complex. Or the transition state. And it is an unstable grouping of atoms that can break up to form products. So whether you're going to form the products or not dictates this hill. And that is your activation energy. So you can go back as being a reactant, or you can overcome that thing and you produce your product. And in this reaction, what is this? Is this an exo or an endo?
Endo.
Endo.
Okay. So in this reaction, you could say this is an endothermic reaction. So when you say endothermic reaction, you need energy here. Okay. So this is the amount of energy that you need. Now, if you're going to reverse the reaction, what it is? Is it still endo or exo?
Be exo.
Okay. So if you reverse the reaction, so this is the reactant, this is the product, that's already an exo. Okay, because your activation energy is just this one. And what will happen to this one? That's the amount of energy that is being released. In the forward reaction, that's the amount of energy here that you need, 85. Not this one. Okay. But in the reverse reaction, this is the amount of energy that is being released. The activation energy that you have is just this thing here. Now, what does this mean in terms of the energy? So for instance, this one. Is this an endo or an exo?
Exo.
Exo.
How about the others? So as you're going to look at this is the energy that it has here. Okay. So in the forward, this is the one that you have. So most likely this is an exo. The AB here, that is your what we call transition state. Okay. So you should be able to identify whether you have an exo or an endo base on the energy diagram. So the backward reaction here, or the reverse reaction, that's the one that is endo. And if you're going to look at this, okay, the activation energy of the reverse and the forward reaction is the same. The only difference is one of them has an additional what? Energy that is either released or absorbed. So here, this is the EA of the reverse. So if you're going to count that on the other side, so this is the activation energy of the forward reaction plus the energy that you have. Okay? Now, how are we going to relate the K with T? So this is what we have. So what can you say about this reaction? Is this new to you? Clue. The one that can explain why the hurricanes has more flood lately than the one before because of the change of the temperature. So how does this Arrhenius equation different from the Clausius-Clapeyron equation? When we have the Clausius-Clapeyron equation, we have vapor pressure. And what we have here is what? Instead of activation energy, you have heat of vaporization. You still recall that? Anyone? Were listening or awake? Are you there?
Yeah.
So see how they do the changes here from this so-called Clausius-Clapeyron equation. Okay, they replace the heat of vaporization with activation energy, and they replace the pressure with the rate constant, and you end up with Arrhenius equation. So what does this mean? The rate constant is directly affected by the temperature. Now, the way you solve this problem is similar when you have this so-called Clausius-Clapeyron equation. I think I have a problem here. So in a series of experiments on the decomposition of dinitrogen pentoxide, N2O5, the rate constants were determined at two different temperatures. At 35 degrees Celsius, the rate constant was 1.4 times 10 to the negative 4. At 45 degrees Celsius, the rate constant was 5.0 times 10 to the negative 4. So you are asked what is activation energy. And once you have activation energy, you are asked what is the value of the rate constant at 55 degrees Celsius. So if we follow the equation that we have here, all we need to do is what? Replace whatever value that is given there. So maybe I put here 5.0 times 10 to the negative 4 per second, divided with 1.4 times 10 to the negative 4 per second. And then the one that I'm looking for. And then what's the R value here? It's energy related, so you use 8.314 J per K mole. And then 1 over the temperature. So I have here the 308 Kelvin minus 18 Kelvin. So what is the answer there that I have for EA? Because once I have the EA, what will I do? I do the same thing, but this time I have a K2 here, and maybe I'm going to use the 1.4 times 10 to the negative 4. And this time I'm going to use whatever EA that I have. So the first equation here, that's for the first problem. The second equation here, that's for the second problem. So I need to get the E here from this value. So what is E? So if I'm going to break it down, I'm going to get another what we call whiteboard. So I have here the ln of 5.0, 1.4. Anyway, they're just going to be the same, okay? Equals to EA 8.314 or 314, and then you have what? 1308 minus 1318. So what do I get here? That's just 5 divided by 1.4. So it's around ln of 3.57. Okay. So what I do, I just get the ln of whatever's the product that you have there, the number. So you have there 1.273. Now, how do I end up with this one? So I have an EA because that's the one that I'm looking for. So I have here 1 divided by 308 minus 1 divided by 318. So I can have an 8.314 here, and the way I have here is that around this one. And then I divide that with 8.314. So I end up with 1.22 something here. Do you follow the math? And if I divide this both sides by 1.288 times 10 to the negative 5, so I will have what? Around 1.03 times 10 to the 5. 1, 2, 3, 4, 5. Or just around 1 times 10 to the 5. Did you get that?
Yeah.
So that's the one that you're going to use if we go back to our previous slide here, because that's the answer that you have here. Now the question is, what is the value of K? Will it be higher than both the one at 45 degrees Celsius and 35 degrees Celsius, or it will be lower, or it will be in between? How do you get the value of K at 55? So based on the relationship, it should be higher than both the K at 45 and 35 degrees Celsius. And if we want to solve it, we can solve it. I'm going to get you another whiteboard here. So I'm going to clear this, and then we're going to work with the new one. So you have here now the ln of K2, and then I'm just use 1.4 times 10 to the negative 4 per second. And then I have already the value here, 1.0 times 10 to the 5. And I have a 3.14. And then this is what? 1308 minus 1328. So this one, I have to leave it at this one, at this point. Because I need to find the value of this side first so that I can eliminate the ln, right? So let's work on this side. So I have 1 divided by 308 minus 1 divided by 328. So I get around 1.9 1.9797 times 10 to the negative 4. And I multiply with 1.0 exponent 5 divided by 8.314. So I get this value here. One, two, three, four. So how will I eliminate this one? I'm going to get the corresponding value here. So this becomes like this. So the E of that one exponent 5 divided by 8.315. I think I made some mistakes. I'll just try to make sure. Please do your own calculation also, just to be sure. 308 minus 1 divided by 328. Now I just have here 2.38. So I have to get that one. E over that one. So I have a K2 equals to 1.4 times 10 to the negative 4, like this. And if I'm cross multiply it with 1.4 exponent negative 4, I will get around 1.5 times 10 to the negative 3 as the K. The value that you should get here, although we round it up, I think we should use the 1.03 or 1.04 from the initial one. Because if we're going to look at the thing here, this is the value that comes out. But because I round this up to 1.0, I end up with 1.5 times 10 to the negative 2. You got that? So I'm not sure if this comes out, but remember, you have the same form of this equation just like your Clausius-Clapeyron equation. So question, before we go to the last topic for this chapter. We're going to utilize the whole time until 1:40, since my daughter has no class this week. So this is just the same as what we call the one that you have before in the Clausius-Clapeyron equation. So the last part that we have is the so-called reaction mechanism. Okay, So if we look at this reaction mechanism, when we go to our balancing chemical equation, okay, what we usually have in a balanced chemical equation is just the description of the overall result of the chemical reaction. But it does not tell us any story on how that equation came into being. Okay, so the balanced chemical equation just tells us, okay, this is your reactants, this is your products. It's just like when you go to travel, okay, you just say, okay, we're going from New York, we go to DC. Okay, from New York going to DC. It doesn't tell us the story. So what happened between your travel from New York to DC? Did you meet some persons from Philadelphia, from New Jersey, or other stuff? Okay, it doesn't tell you that story. It just tells you, okay, I came from New York and went to DC. But how the travel from that to the places, it doesn't tell the story. So the same thing with the chemical system. A balanced chemical equation, these are the reactants, these are the products. So if you want to know what happened in between, the reaction mechanism is the one that will tell you the story. Okay? So if you look at each of the reaction, usually it's not only made up of a single step. Some of them has more than what? One step. Okay? It's rare that you only have one step reaction. So usually that set of steps that you have, that's your reaction mechanism. So we could say the reaction mechanism is just the route of travel followed during a trip. Okay? So each step of the reaction mechanism is what we call an elementary reaction, and usually a single molecular event. So if we're going to look at the set of the elementary reaction, which then give us the balanced chemical equation, that is your reaction mechanism. And this is the one that makes what? Your orgo challenging. Why? Because you are asked, okay, by the so-called electron pushing. What's the reaction mechanism from this reactant going to this product? And then you have to show the different bonding that breaks and the different bonding that form. Okay? So in this, what we call reaction mechanism, you have this elementary reaction. So that's the each step or single event that happened. Okay? Now, if you're going to look at this single event that happened, some of them are so fast and some of them are slow. And the one that's slow, that's the one that determines the rate law. How fast your reaction will be is limited by the slowest reaction. How do we apply this rate determining step in real life? So if you are in a freeway, how fast you drove there is determined by what? The traffic that you have. Okay? If you are in a cafeteria, I don't know if you experience this at this time of COVID, how fast the lane would move depends on the person who acts slowly. Okay? So the rate determining step, that's the lowest step. That's the one that gives you the rate law for the reaction. So by now, okay, before you learn, rate law can only be what? Determined experimentally. But after this discussion in reaction mechanism, you should be able to tell that you can also determine the rate law by just looking at the slowest step in a given set of elementary reaction. Okay? So the way we look at this, a reaction mechanism cannot be directly observed. However, you can determine the rate law by the experiment and decide if the reaction mechanism is consistent with that rate law. Okay? And the rate of the reaction is determined completely by the slowest step, which is the rate determining step. Okay? So, how we look at this rate law and reaction mechanism. For instance, you have a reaction of NO2 with F2. And these are the following elementary steps. Okay? So if you follow this thing, the sum of your elementary steps, that's your overall reaction. So if we're going to add these two, so if you're going to make it like this one, so what can be cancelled here? Any more that can be cancelled?
No.
I canceled something that is found in both the reactant and the product side. So you have here an F in the product side, and then you have here an F in the reactant side. So when I add these together, this is my overall reaction. Do you follow? Now, the one that being asked here is, as I've told you, I can determine the rate law by just looking at the rate determining step. So the rate determining step here is the slowest one. So what will I do? I put the rate, I put the K, and the concentration of all reactants in that slow step. So I have it like this. And that is my rate law. Analyze. And if it's not clear, you can ask question.
I'm confused how you knew that that was the correct rate law.
Because I base it on the slowest step. And all I did is just write up the reactants that it is in the slowest step. So what can you find in the slow step there? The NO2 and the F2. So that means the speed of this reaction depends on this step, how the NO2 reacts with F2. Now, you may ask yourself, what is that F? That's what we call an intermediate. So an intermediate is a species that is produced during the reaction that does not appear in the net equation because it reacts in a subsequent step in the mechanism. So when they're doing the experiment here, during the reaction, they found out that F is present. But they cannot find it in the overall equation. Okay? So we could say an intermediate is something that is produced in the initial reaction and used in the subsequent reaction or elementary step. So how do you determine if you have an intermediate? You have a species that is produced in the initial step, in the initial elementary step, and then that species was used in the succeeding step. That's your intermediate. Easy to find? So maybe I'll borrow a question to see if you understand from another book. Yeah. So let's try to answer this one. So to see if you understand the concept that I'm discussing to you. So write the overall equation, identify the intermediate, and what can you say about steps 1 and steps 2 with regards to the given step, given the rate law is K and 2O. Analyze. This is not in our material, but I just want to introduce this to you so you will understand more about it. So which do you think is the fast and which do you think is the slow reaction? Is it step 1 or step 2? So this is your rate law. So what do you think is this one? Slow or fast?
Fast.
Is that the fast? Where do you find only N2O? You can only find N2O on that. So step 1 is the slow. You follow there? Because based on this one, this is your rate determining step. Why? I have N2O here and oxygen, but here I just have N2O and the rate says it's just based on the N2O. Everyone follow that? So if I'm going to write the overall equation, how does it look like? I cancel this, so I end up with what? N2O2 plus N2 plus oxygen. Are they balanced? Yeah. So I have here 2 N2O producing 2 N2 and oxygen. Do we have an intermediate? What is the intermediate? Anyone?
Is it oxygen?
Do we have an intermediate here? Okay, so the intermediate is oxygen. Because that's the one that is produced. And in terms of this one, we could say step 1 is lower than step 2. Did you follow that?
Why is step 1 slower than step 2 again?
Step 1 is slower than step 2 because the step 1 is the basis for your rate law. The slowest step is your rate determining step. Okay, you follow that? Before we go back to our former slides?
Yeah.
So we have the intermediate. Now, what is the case of the so-called catalysis? Okay, so catalysis is just the increase in the rate of reaction that results from the addition of a catalyst. And the good example of these catalysts are enzymes, are so-called biological catalysts. Okay, So when we're talking about biological catalyst, what we have is what we call anything that makes the reaction faster. So for instance, in the enzymes, okay, uh, why do you have this so-called lactose intolerance? What is missing for those children or for those people like me to have this what we call lactose intolerance? We don't have the enzyme lactase. So we cannot break down lactose. Because lactose is made up of what? Glucose and galactose. Okay? And this enzyme also, we could say, differentiate us from the animals, the so-called ruminants. What do these ruminants do? Isn't our class supposedly until 140? Okay? So I expect no, we could say conflict because ideally we are until 140. I don't know why you're asking that you have to leave because you have a lab. I'm just using our time. Okay? So, what differentiates us from the ruminants? So, ruminants usually when they eat fiber, they can break it down, right? But people like us, when we eat fiber, what happened? They remain as fiber because we don't have any enzymes that break down fiber. What's the enzyme that break down fiber? Anyone? That cows and goats have. Okay? They have the ability to break down cellulose because they have cellulase. For us, we don't have cellulase. That's why when we eat fiber, it will get out of our body also as fiber. So when we have a catalyst, it's anything that makes the reaction faster. And how does it do the make it faster? Usually, it increases the reaction rate by providing an alternative reaction pathway with lower activation energy. And when the activation energy is reduced, your K increases exponentially. That's why if you're going to look at the catalyzed reaction, this is how it looks like. Catalyzed and uncatalyzed reaction, this is how it looks like. Alternative pathway. And that's alternative pathway. Usually, they have lower activation energy. Okay? Now, how do we incorporate this catalyst in our materials here? So consider this reaction. NO2 reacting with CO, producing NO and CO2. So if you're going to look at the elementary step, this is how it looks like. Okay, so you have this first step, which is slow step. You have the second step. Now the question being asked here, is there a reaction intermediate? Write the rate law. And what is the catalyst in the reaction? So there's an additional form here. Do we have an intermediate here? Yes or no? Anyone?
No.
Do we have an intermediate here? So what's our definition of intermediate? Produce and use. So you have an NO3 here that was used as NO3 in the next step. Okay? So that is our intermediate. Before we answer the rate law, how do we define catalyst here? So if we have your intermediate as the one that is produced and then used, for the catalyst, that's the one that's used and then produced. So what does this mean? You have it initially, and then you're going to have it at the next step. And if you're going to write the overall reaction, it's not there. Okay? So the question is, do we have a catalyst here. Okay, the answer is we don't have any catalyst. Because if we're going to look at the reaction here, okay, maybe we can cancel this out. But you could see there's still the same species that is similar to that. Because if both of them are canceled out, then you can consider it as a catalyst. But it's sad to say that you have what we call 2NO2 here. So there's no catalyst here. And then you have an intermediate here as NO3. Now the question is, what is the rate law? How are we going to write the rate law here? So rate is equals to what? K producing you follow why this is the rate law? Everyone follow why that's the rate law? Because that's the slow step. And what you do when you write the rate law, just write whatever reactants you have. If you're going to write it, this is really in this form, right? But you know, NO2 is the same as NO2. So NO2 times NO2 is just NO2 squared. So we could say this is what? A second order reaction. Do you follow? Everyone?
Yeah.
Because you might be answer, how do we know if it's a second order? So this is the example of a second order reaction. So we don't still have an example of this catalyst, but the last slide that I have here, this is a Nobel Prize winning equation. So you're asked here to write the rate law for the first step in the mechanism of the decomposition of the ozone. So if you're going to look at this one, okay, if it says the first step, so that means this rate is just equals to Cl times what? O3. You might ask, where did you get this, professor? It says there that write the rate law for the first step in the mechanism. So this is the first, and this is what we call the second. Okay, and then how this becomes this what we call the thing that I have said. When you add this together, what will happen? What is the overall equation here? Do you have an intermediate? Do we have an intermediate here? The answer is yes, this one, right? Do we have a catalyst here? The answer is yes, this one. It was there, it was used up, and then it was produced. So that is your catalyst. Now overall equation, what do you have? So you cancel this, you cancel this, you cancel that one, you cancel that one. So you have what? Ozone reacting with oxygen to produce 2 oxygen. That's the award-winning reaction by Mario Molina, who passed away unfortunately last year. He's trying to explain the greenhouse effect there, how ozone is being destroyed by CFC. So before someone put the Gorilla Glue to make their hair stable for some time, we have this spray net when I was young during the 80s. And if we use that spray net, it will make our hands stand still for a while. That's why you see some of them as a hair like that one. Okay. And they found out that spray net contributes to the destruction of the ozone layer. That's why they phase it out. So we have the CFC problems that we have. So here you're able to see your Cl there, that's your catalyst. Okay? The Cl atom. You don't see it in the overall equation. How is it different from your intermediate? It was used and then produced. Intermediate, it was produced and then used. So the chapter ends here. And this is where the coverage of your first exam next week will end. So question, it's still the same as the one that I did. Okay. So I just going to what we call do this as a recorded slide. So question. Question?
All clear.